Welcome to Control System classes. The topic for today's discussion is Integral Controller from Electrical Engineering JOC. The integral controller is going to be inserted in the controller place, and the controller output is actuating signal, the input is error signal. So it is an integral controller. The output actuating signal will be the integral of error signal. So let us write an equation. U of t actuating signal is proportional to integral of error signal E of t into d into t dt. To remove the proportionality symbol, let us add a constant ki, where ki is called integral gain constant. Take Laplace transform on both sides and rearrange the equation to get the transfer function form. So transfer function is u of s by e of s is equal to ki by s. So let us represent the controller as a form of k by s or ki by s, and the plant usual notation is g of s. And the main advantage of using integral controller is it will minimize the steady state error. Let us verify how it will minimize the steady state error in the forthcoming slides. Here, the controller is given with the function k by s. The plant is 1 divided by st plus 1. The input r of s is 1 by s, and it is assumed with unity feedback system, and h of s value is 1. Now let us write the feed forward function by multiplying the two blocks in cascade. So the feed forward function is k divided by s into st plus 1. Let us calculate the error E of s. The error E of s is given by R of s divided by 1 plus G of s into H of s. H of s value is 1. Substitute the feed forward function in the place of G of s, and R of s is 1 by s, and I got this equation. Now let us calculate ESS in S domain. So ESS in S domain is limit s tends to 0 s into E of s. For the E of s, I have taken this equation and substituted here, and I have substituted SS1. On verifying, I got ESS, the steady state error becomes 0. It means I can conclude that with introduction of an integral controller K by S, my steady state error is 0 here. So this is the main advantage of going with integral controller. And let us calculate now closed loop transfer function. This is my open loop transfer function. This is my feed forward transfer function, and I had written C of S by R of S for the given blocks. I have reduced the blocks, and I had written C of S by R of S is K divided by S square into T plus S plus K. Now let us compare equation 1 with equation 7. Equation 1 is of first order, equation 7 is of second order. Now we can able to conclude that this integral controller has increased the order of the system by 1. With increase in order, the stability may decrease. So that is one of the consequences of introducing an integral controller. Let us check how to realize this integral controller with op-amp in the next slide. So what is the overall conclusion we had discussed so far? The integral controller reduces the steady state error without any manual reset. So it is also called automatic reset. The integral controller is also called automatic reset. The integral controller always increases the system order by 1. With higher order, if we have more poles, so it may results in instability of the system. That is the consequences with introduction of integral controller. Let us realize an integral controller with an inverting integrator. As it is an integral controller, we have taken an op-amp, and the operational amplifier is connected in integrator form. So input resistance is R1, the feedback resistance is C1. The next block is called sign changer, as we have used an inverting integrator, right? So the equation of inverting integrator, which is connected in the first stage, is the output U1 of t is equal to integral of E of t. When we executed the calculations by applying KVL and KCL, we got the final equation as U1 of t is equal to minus 1 by R1 C1 integral of E of t into dt. On taking Laplace transform, we get minus 1 by S into R1 C1. So this is a stage 1 transfer function. Stage 2 is U of t by U1 of t. As it is a sign changer, both resistance values are equal. So it will provide the value of -1. The overall transfer function is u of t divided by e of t, or in S domain u of s by e of s. Multiply the both answers. So we get 1 divided by s into r1 into c1. So by adjusting the value of r1 c1, we can able to vary the overall transfer function, and hence the stability or the effect of poles will change based on the values of r1 and c1. The integral gain constant Ki for the given structure is 1 divided by R1 into C1. Thank you.